Hi, so I am delighted to welcome you to the second of our virtual tours of a New South Wales research facility. And I'm delighted to have with me Professor Gordon Wallace of the University of Wollongong. Where are we, Gordon? What is this place that we're about to visit?
First of all, welcome, Tim, and welcome everyone else. We're here on Wollongong's Innovation Campus. As you can see, we're about 200 metres from the beach, over the trees, right over my shoulder at the moment. We've been here for about 10 years, and we're going to visit bits of the Intelligent Polymer Research Institute, and that acts as the headquarters for the ARC Centre of Excellence for Electromaterial Science, and also the ANFF-supported node. And there's a few other little things we'll introduce you to as we go through.
Now, Electromaterial Science, that sounds pretty cool. And what we're hoping for as well is the relevance of space, right? We're hoping to get you flown in space. We're hoping that your research team are making things that are going to go up into some of the missions that are coming up that Australia is working on. We had a very exciting announcement this morning of an extra $65 million for the Australian space ecosystem. So hopefully we're going to get some of that money is going to go to more flights, I understand. So maybe we can get you aboard some of those.
Yeah, I think you'll see that the focus of my research is on the discovery and development of new materials, but then using those amazing discoveries in areas of energy and health, and they have to be related to space, right?
Energy and health, absolutely. If you don't have power in space, you're dead, and we're hoping to send people to Mars and beyond. So that's going to need a lot of help, I'm sure. Now today, the pictures are being brought to you by Sam Finlay from the communications team. He's holding the camera for us. If you ever have an issue and you can't hear us, just let our team know. Heather and Madison from SmartSat are in the co-hosting chair, and just let us know if you have any trouble hearing, and we're happy to repeat stuff today. And of course, we're also recording this session. You can send us through questions on the chat. And you can also talk to one another if you want to formulate a question together. And this session will be published on our YouTube channel as soon as we can top and tail it. And hopefully it'll become a record. And the first of a number of these virtual tours that we're going to do. This is in real time. So we're going to be walking around. We're going to be talking. So where are we heading to next?
Let's go there to the first lab, and I'll introduce you to some of our colleagues.
Fantastic.
As I mentioned, we are working on the discovery and development new materials. And the first stop that we'll have, we'll actually talk about a newly discovered form of graphene. We all know that graphene is an amazing material with amazing properties. It's not very processed, and our team has discovered a way to overcome that challenge to make graphene. And he'll tell you everything about the amazing graphene story.
Hi, nice to meet you. So we start making graphene from this graphite here, essentially. Graphite's just a pretty basic rock. It's used in pencils and whatnot, and that can be split up into its layers. They're like chicken wire that all stack together. They can be made into a processable powder. So I'll just put some here so you can see. It's just essentially, a little powder. That powder, unlike that rock, can be easily dispersed in water and also in tow. And so it makes nice dispersions. Those dispersions mean that it can be easily put into a variety of different polymers. So here we have HDPE, so a very non-polar polymer. And here we have latex, which is a water-based polymer. Typically, you would not be able to do that with graphene, especially in the loadings that we have here. So this polymer here, which is still flexible and nice, and I'll show you it's stretching as well.
Now, Sam, just quickly, Gordon, can I get you back in the shot just quickly? Now, we had a little break when we entered this room. What is this lab again? Just give us a quick.
So here in this lab, we're looking at where we discover new types of materials. Graphene is one of those examples that Greg is speaking about. And then I want to highlight that discovery is coupled with utilization of the amazing properties that graphene displays. And we're going to look at some of those applications in energy today.
And we're talking with?
Greg.
Beautiful. Okay,
Greg,
keep going, Greg.
Greg, the king of graphene.
Yes. So this latex is really interesting because it has excellent conductivity. The resistivity is about is less than 100 ohm per square, and it's still retaining excellent mechanical properties. And we've done that even in PDMS. That's 50% graphene. So 50% of that rock, and we're still nice and flexible and stretchable. So it's a very nice material. And we're looking into some sensing applications for that. Next up here, we have another of the very strange properties of graphene, in that a small amount of liquid will form these dough-like structures here. So that dough can be shaped and bent, and you can do whatever you want with it. So here we've packed it into a little structure. And if you put a membrane on top of this and then pack two of them together like so, we can charge that up just with a simple phone charger. And then run. That's wrong way. Sorry, haven't charged that enough clearly. Yeah, but that can run motors and LEDs and whatnot. The motor is the more impressive one, but I should have got an LED. And then next up, because that dough can be moldable and whatnot, it can also be made into a nice thin film. So here we have a titanium foil, and then onto that has been pasted some of that dough, and that gives you, and then between that a membrane, and then two more like in that same stack, and that gives you a flexible supercapacitor. So these supercapacitors can then be put onto the back of flexible solar cells. That means you get a nice flexible overall material that can not only generate but hold electrical energy. So
Greg, we had a question
Sure.
from we had a question from one of our participants, Christoph, and he asked, graphene in latex, can it be similar to carbon fiber in terms of RF reflectivity, so relevant to antennas and so forth?
Possibly, yes. Yeah, there's no reason that would not be the case. It's just about like putting in the amount that you need, essentially. So that's a really high working. So that'll be much more conductive. Like that'll be very, very conductive. So yes, there's no reason why we couldn't try that.
There's an interesting application that Christoph pointed out, which is it could be useful for inflatable reflectors, which is something we're kind of keen to understand in terms of space traffic management, communications, a whole range of other things. So thank you.
Interesting. Thanks.
And just adding to that as well, because of that form that we got the graphene in, it's actually highly processable, as Greg has explained, but also we can fabricate other structures, 3D structures, using 3D printing, for example, to create unique properties from the materials. Thanks, Greg. So we finished up there looking at the use of graphene in an energy device, the flexible solar cell, and the capacitor on the back of that solar cell. All of that can be made with reel-to-reel printing, and we do that in partnership with our colleagues at Newcastle, who are another part of the ANFF-materials node, with Professor Paul Dastur. So we've got not only the materials capabilities, but the fabrication capabilities to make real devices and real structures. And we're going to just move down into the laboratory a little bit and have another look at.
Thank you, Greg.
Yeah, thanks very much. Have a look at another use of new materials in energy devices, and this time it's thermoelectrochemical devices. So devices capable of turning waste heat into electricity, or any form of heat into electricity. And I'm going to introduce Jun Chen, who's going to tell you about our fascinating work in this area.
The main thing is we want to work is we're using the temperature difference.
Oh, Jun, would you mind taking off your mask just while you speak? And then, yeah.
Okay.
Thank you very much.
The main thing is we try to use the recipe is use the temperature difference between two electrodes. Then we could use this delta T temperature difference to generate a voltage. This kind of voltage can be used to charge, can be harvested through the temperature difference and charge the battery, charge the supercapacitor, which can be further developed into a wearable device. The major issues for the wearable device, we need to develop the gels first, like the gel has to be in-house developed combined with the materials, which is very mechanically strong, and we can easily hold it, which is we call double network gels, which has been developed in-house. And combined with the material developed by Greg, as already people said, that we can make something device set up, so a testing platform, and combined with gels, we actually can make these flexible materials, which you can have a bend styles. So we can, and not just the flexible materials, it's also you can harvesting your body heat, which is normally said because the body has a certain temperature stable from 35 to 37 degrees, generates the temperature difference compared with the environment.
So can I confirm? So this material here, a flexible material, and what you're saying is that because of the body heat of the person and the difference between the body heat on one side to the other side, that generates an electric charge.
Yeah, exactly.
Okay,
so
fantastic.
Here the thing I can show you something, which is if I set up a 0 when I connection, because we can control the temperature difference, it geometrically can see the voltage has been generated based on three different devices.
Where's the temperature difference here? Can you point that out? So
this is from one side to the bottom.
So
this is a control panel.
So this is literally colder, very slightly colder than this.
And if you put your hand here, you can feel this is when we try to cooling one side of the electrode.
Okay.
So this is one thing. And the other,
I can feel a little air coming out.
Because we try to cool one side
and
maintain the other one. But the other interesting thing here that we can do is we're not just using the body heat or environmental heat. The other thing that we can actually use is we call the solar heat. Because solar heat is a wavelength not really has been used because they are not high power enough compared with traditional solar cells. All right, solar heat is the ones which you also can be absorbed by the materials. When you show the lights on, we can see that voltage has been generated just to show the lights on, because this is a wavelength by the graphene, actually developed by the graphene. This graphene is kind of thermal conductivity, so which can transfer the heat and also can absorb the heat for the solar wavelengths.
And now, is that a photovoltaic transfer or it's still a thermal transfer?
I think it's still the thermal transfer because the wavelengths over 600 nanometers cannot really be used as a solar cell, which we call is high intensive energies. But this is the wavelength which normally generate the radiation, the thermal radiation things, but they are low energy, but that's heat normally has been used. But it might be interesting in the space technologies because when we are outside in the space, there are lots of wavelengths in this area, potentially can be used, developed in the wearable device can be developed in there.
So potentially an astronaut could have a spacesuit that actually powers itself.
Yeah, that's going to be a combination with radiative thermal energy harvesting combined with wearable supercapacitor and battery developed for the persons, and could be a combination technology which need external expert combined with expert in our labs, so which has the potential to be a package development.
So I think this is a great example of this project that shows that we can take the most recently discovered materials and coupling that with the most recent advances in fabrication. Jun and the team have been able to create devices and structures that are actually practically useful. So just the discovery of the material by itself is great, but the ability to fabricate devices and structures in order to tap into unusual energy sources or energy conversion phenomena is all brought about by the ability to fabricate.
Now, we had one interesting observation and question by our audience, which was one of the things you can do is create a solar concentrator type steerable antenna effectively, but it concentrates the light of the sun into a central point. Could you use this for that?
We might be able to, but depends on that. If that's the energies or sunlight we want to use, then we might be slightly develop or change the material setup because we want to match together sometimes. So light intensity is also affect the device performance. But I think that's the most benefit is that we are part of ANFFs. So the ANFFs provide all the facilities for us to do a special design. So then we can quickly try our demo or our original design to kind of test our concept is working or not. So it's the most benefit for this lab.
And that acronym ANFFs, what does that stand for?
They called Australian National Fabrication Facility.
Beautiful. Yeah. Thank you so much.
Thanks, Jun. And and as Jun mentioned, and I mentioned outside, we are the headquarters for the materials node of ANFF. And you can see that ability to create prototypes is really critical to rapid development of new discoveries in material science. And that's also true in our electrolyzer technology program. and we're going to look at how our ability to create prototypes, again, using our facilities, has resulted in rapid developments in our electrolyzer technologies to produce hydrogen, for example, but also fuels from carbon dioxide. And to explain those areas, I'm going to introduce you to Klaudia Wagner.
Hello. Our group actually has quite a lot of experience in devices because we did in the past solar cell, fuel cell, and different types of electrolyzers. You can actually see on this bench and all the devices which were made here. And you can imagine that actually this knowledge can be easily translated from one device to the another. Hysata is a new spin company which is developing a new technology for the water splitting. Aquahydrex, it was the previous one, and it was also born in this group and still exists. And the electrolyzers of Hysata is the combination of the best, which we learn across the years in these different devices, and is offer a high efficiency. And the high efficiency and the simple design structure is actually offer the possibility to produce hydrogen at the level of $2 per kilogram, which is kind of appealing to speed up this zero net targets, which we have in mind for our future. It was all possible because actually we have the capability here, from the simple machinery in the workshop, laser cutters, to this very sophisticated 3D printing technology in TRICEPs, which the guys in the TRICEPs can print in plastics, and also they can print in the metal with high precision. And actually, this is quite important because if you have the capability of the structure for your electrode scaffold, it matters for the mass transport going through the electrode. Just to give you the example from the water splitting, if the water has problem to get into the electrode and penetrate into, and if the gases which are produced in the electrochemical process, like the hydrogen and the oxygen, have some difficulty to depart from this electrode, this all will create some resistances which will harm your Faradaic efficiency. In other words, if you want your cell to be high efficient, you have to take this into the consideration. And from the design point of view, it's also very important because your cell is not going to work alone in the industry. Your design and your cell has to be designed that will be able to work in the stack configuration and also to be able to be scalable. It means, in summary, to get really to the target of the $2 per kilogram, and everything matters.
And so thank you so much for the explanation. And it seems, is it true that this is also a general purpose system? You can adapt it to different kinds of anodes and different kinds of electrical systems, different kinds of chemical processes?
Absolutely. If you imagine the whole system have two electrodes and have the electrolyte between. It means you of course change the catalyst, but the principle, if you learn, you can really translate and just pass.
So one of the things that we have heard about is people experimenting with gels, for example, as the transport mechanism for the ions, and gels that might be stable across a very wide range of temperatures, and particularly interested in batteries that are small for very small satellites. I think if somebody in our audience or viewing this online is interested in saying, okay, I want to develop a new kind of space power battery system, is this the kind of thing that you guys are hoping to achieve? You'd like some partners to work with you?
I think absolutely. It means it's possible. Yeah, we were working with gels electrolyte before, and it's absolutely possible.
Fantastic. Thank you so much.
Thanks, Claudia.
Have a little bit of a close up on the different kinds of 3D printing that we've got here. Very interesting. And all fabricated here using 3D printing capabilities, so arguably could be scaled up. Thank you so much.
Thanks.
Thank you.
Thanks, Claudia.
Do one more wide shot. Get that poster in there. So there we go.
Losing me.
Fantastic. There we go. I'll take a camera shot here. Fantastic. Thank you.
I think as both Klaudia and Jun have pointed out, the ability to rapid prototype coupled with the most recent advances in the materials discovery can really have a big impact on a range of applications in a much shorter period of time today than this would have been possible even 5 years ago. So, and as Tim mentioned, we're more than happy to work with others who have discovered other materials that might be useful in devices like these and to help advance your discovery into practical devices in as little a time as possible. So we're just going to change tact a little bit now, Tim, and have a look at what we're doing in the area of 3D bioprinting. So this is more emphasis on our health examples. We'll look first of all briefly at some of the commercial 3D bioprinters that we have at our disposal. And then we're going to walk over to TRICEP to have a look at what they do in terms of 3D printing and customized printers and customized materials for printing.
And TRICEP is?
TRICEP is the Translational Research Initiative for Cellular Engineering and Printing. Right? I should have made that a competition. I mean, whoever got that right, we could have given them a prize, but that's what it is. So let's have a quick look at the commercial 3D bioprinters, and then we'll walk across the road to TRICEP. So this lab contains a range of commercially available 3D bioprinters. Technology laboratory just on the other side. Stem cells are used very frequently in 3D bioprinting to treat medical conditions. I've asked Johnson just to give you a look at just our most recent acquisition of a commercial 3D bioprinter.
We have a variety of 3D bioprinters supported by ANFF, and these 3D printers allow us to print a variety of different things, including customizing things made in-house. 3D printing systems such as the EnvisionTech and GSIM allow us to print multiple inks simultaneously in a temperature-controlled environment and cartridges. We also have a digital light processing system from Solink that allows us to print small features, about 3 to 4 millimeters, but very high resolution of microns and layer spacing.
Is it true that you can use almost any kind of material as an ink?
Yes, any kind of material, as long as we call it printable. It has the right rheological properties, and it has the right bioactivity that can induce the required cell effect. So the newest equipment that is joining our suite of bioprinters is the robotic arm printer from Advanced Solutions, and this allows us to print on a non-angled surface without the need of a support material. It also is equipped with an automated function that we can plan the workflow, so we can pick up and dispense or liquids. So basically automating the cell culturing process.
And this is actually a 5-axis or 6-axis?
6-axis robotic arm that can do at any angle. So it really is beneficial compared to the other 3D printing systems that you always have to print on a horizontal flat surface.
So theoretically, you could have any shape at all, and you could print something on the outside of that shape.
Yes. The most challenging bit is, of course, a non-contour sphere, and you can basically print on top of that without the need of building a support material from the baseline.
And we're now going to head over to TRICEP, as we mentioned, and look at some customized printers. And one of those customized printers is actually based on a robotic arm, but that arm controls one of our printing devices, and that project is for printing directly into burns or wounds for skin regeneration, work that we're doing with Professor Fiona Wood in Western Australia. So let's go grab our umbrellas, Tim, and head over to TRICEP.
Thank you very much.
Thank you. Thanks, Johnson.
TRICEP is established by URW and is supported by the Australian National Fabrication Facility through the Materials Node. TRICEP is established to facilitate the translation of fundamental advances in 3D bioprinting into real clinical solutions. As such, we work alongside clinicians from around Australia, indeed around the world. These clinicians and collaborative projects include Professors Peter Chung and Claudia Wagner, working on cartilage regeneration in the knee. Dr Payal Mukherjee on 3D printed ears, Professor Toby Coates on the creation of 3D printed scaffolds to improve the efficacy of islet cell transplantation to treat diabetes, Professor Gerard Sutton in pursuit of the bioengineered cornea, and Professor Fiona Wood developing 3D bioprinting protocols for skin regeneration, and in particular, the treatment of burns. Each of these endeavours requires the development of customised bioinks and bioprinters in a way that ensures seamless transition into a larger scale manufacturing environment when required. The TRICEP team, supported by the University of Wollongong and ANFF, has in place the expertise and facilities to help fast-track your ideas in 3D biofabrication. We can assist in the development of customised bioinks and 3D bioprinters. Our established clinical network and links to others with expertise in health economics and mapping the regulatory pathway provides insights that can set projects up to be translation ready. So please, do not hesitate to contact Pete, Sanjeev, Steve or I if you have any questions.
This is TRICEP, and
Let's go and stand in front of the panel here.
yes, well, you can see what we do here: sourcing the materials, formulating the bioinks, customized hardware, so designing, developing the protocols, but most importantly, working with clinicians in order to develop their clinical protocols. So we'll go through and we'll meet up with Sanjeev and Steve.
Let's introduce our host here.
Steve.
Good morning, everyone. My name is Stephen Beime. I head up the additive fabrication capabilities.
Steve, can you take off your mask for us?
Indeed.
And we'll get you to say that again. Sorry, thank you.
Good morning, everyone. My name is Stephen Beime. I head up the additive fabrication capabilities here in TRICEP.
Fantastic. Thank you so much. Take us through.
We're just going to walk through and catch up with Sanjeev, and then Steve's going to show us the amazing stuff we have in that additive fabrication capability, both in terms of commercially available printers, but also our customized printer program. So this is the bioinks area where they've been sourced, brought in, functionalized, formulated, sterilized and packaged. And heading up that activity is Sanjeev Gambhir. And Sanjeev will give you an example based on materials that we get from Seaweed, from a local seaweed producer.
Hello. Here we are producing a TRICEP wide range of bioinks for different medical applications. So the important thing is the quality of the starting material. We have been working with the primary producers, including Australian seaweed farmers, to source this starting material. The important ones are Ulvan and Alginate. Ulvan is going for wound healing applications, and Alginate is also for cartilage regeneration. These two important ones are the key starting materials which we have been using.
And this, sorry, can you say that again for us? So this one is used for
wound healing applications.
Wound healing, okay.
And this one is for cartilage regeneration.
Cartilage, wow. I needed that when I hurt my knee.
Sure. I need to as well. So first step is the chemical functionalization. As such, these materials don't meet with the right rheological and mechanical properties. So we are doing first the chemical modification, developing the processes on the laboratory scale, and then taking the process to produce kilogram quantities here. During the entire process, we are doing strict quality control and monitoring the process and checking its quality.
So these bioinks you're manufacturing, of course, I guess they have to be approved by the Therapeutic Goods Association Authority, the Federal Drugs Authority of the US. Is that correct?
Yes.
They want to be, you want to use them to make parts that go into bodies for medical. Okay.
So what we have been doing here is we are, once the process is developed, we are optimizing the conditions for its storage, and also doing the shelf life stability study, which is an integrated part of the materials which we are going to use it. And over to that, we are these products are temperature sensitive as well as light sensitive. We are developing scalable processes for the sterilization of these bioinks. And the entire process is documented as per quality control management systems, and we are moving towards acquiring ISO 13485 certification for this facility.
So if, for example, we had a situation where you had astronauts in the Artemis lunar station, or even astronauts on Mars, and they injured themselves in some way, they had a laceration or they had an injury because of, you know, some kind of stumble or trip or something, could you use these kinds of technologies to treat them?
Yes, this will be a very interesting area to explore further, and definitely these materials will have potential for these type of applications as well.
Very exciting.
Yeah, and the processes that are developed at TRICEP are now scalable to take the technology for commercial production.
Very cool.
Thanks, Sanjeev. And as Sanjeev mentioned, we're setting up quality management systems in order to head towards ISO accreditation. And as Tim alluded to, all of these bioinks, coupled with the customized bioprinters, are all set up for point of care use. At the moment, that point of care is in the hospital, and we'll be setting up bioprinting capabilities in the hospital. But obviously, the great advantage of these protocols is that they're extremely deployable in a wide range of areas. So we might just walk through and catch up with Steve again, who's going to show us about the printing technologies.
Okay, good morning again, everyone. And today I'm just going to give you a very brief overview of some of the additive fabrication capabilities that we have and the purpose of having this large suite of additive fabrication tools and how we're using it to develop the next generation of bioprinting hardware. So as Sam zooms around, and we'll walk along with Sam, we do a bit of a pan across all the equipment, you can see that there's a fleet of state-of-the-art tools that are employed within the facility here. We started off 3D printing in about 12, 13 years ago. And with that, we were supported by Incris to allow us to get the first round of state-of-the-art printers. That covered FDM extrusion, polyjet printing, and metal printing systems. So now, as we continue to evolve with the state-of-the-art, we're moving into full color printing systems, ceramic printing systems, as you can see here behind me as well, and a range of high melt temperature extrusion systems to allow us to do engineering grade materials such as PEEK or medical grade PEEK. So we have this suite of tools. We're working very closely with clinicians, but clinicians will come to us and they want to be able to deliver materials such as those that Sanjeev has described in the point of need. We have also a fleet of bioprinting tools, so large scale bioprinting systems. However, as soon as a clinician identifies a project, we can also identify that the software that hardware, the printer has is incompatible because it can't modify it, or the hardware itself is incompatible because we can't modify that either. Otherwise, we can infringe on maintenance agreements and whatnot. So that's led us to have to develop our own printing solutions. We have a range of these on display here in front of us, and going from open source bioprinting systems right through to handheld points of delivery devices. So the example case being here, where a number of years ago, we had an issue with one of our flagship bioprinting systems. It was supplied by an overseas company. We needed to produce a range of scaffolds and deliver those to collaborators in Italy in a very short period of time. The printer had died for a very nominal reason. An encoder had been broken by one of the staff who was cleaning it down using ethanol. We weren't allowed to replace that encoder strip, so we ended up having to produce a printer to allow us to harness a 3-axis stage, couple that with a glue dispensing unit, and use that to extrude hydrogel materials into a scaffolding structure.
Now, whoa, Steve, now tell us, you've got several different little containers here. So you're saying you don't just print ink, you print other materials to create a substrate?
Yeah, so when I say ink, I'm referring to a biomaterial ink. That biomaterial ink is made up of the gel or the alginate materials that we prepare in the adjoining laboratories. And what we would want to do, because biology isn't just homogeneous, it's not just one structure of material. We want to be able to incorporate different growth factors or different cell types within a multi-layer structure. So in the case of the example here, it's being used to work towards replicating the living ear, where we would have a rigid or higher strength reinforcement polymer like polycaprolactone, and seated around that we would have the cells contained in the gel materials that allows them to grow, proliferate through the structure. And then we can also have a supporting structure, a sacrificial supporting structure that we can then use to dissolve away and leave us with the overhanging structure of the ear.
And you've got a model of a human bone here, is that right?
This is actually quite an old model. This is used to demonstrate what we thought we would do many, many years ago when we first purchased a metal 3D printing system. And the model itself is about 13 years old and has survived the test of time on many, many displays and tours. But this allows us to show how you would have a modified titanium screw as a fixation device, which could have incorporated a drug-eluting polymer.
So a drug inside the screw itself.
Yes.
And the kinds of process that you went through to develop this bioprinting, is that similar if we were to say, okay, we want to do printing of material structures or even tiny structures on the moon using Martian regolith, for example? That's a chemistry process that's similar to the processes you've developed for bioprinting?
Certainly, you're starting with a raw material, you're processing that raw material so that it has physical properties that are compatible with the printing system. Now, having said that, you've got to design the printing system so it's compatible with the initial raw material properties, and that's what we've done in this case. So extrusion printing is used for hydrogel materials. We would use microvalve jetting for low viscosity inks where we want to put nanoliter depositions within a structure, and we can use a range of other printing and deposition techniques compatible with the material. What I'd like to do now is hand off to Kalani, who's going to give us an overview of one of the handheld devices that we've developed, which can be used in a remote access location, and then the training protocols that we've developed around a lower cost bioprinting solution.
And Kalani, you might just also mention how Steve and yourself and the team, we work very closely with the end user to transfer the design materials and the design printer, in this case into the clinic, but with anyone that we're working with. So we have a very well-established training program to introduce those new technologies to the end user. And Kalani is an important part of it.
And do tell us about your role here, Kalani.
Yeah, thank you. So as Gordon and Steve mentioned, we work very, very closely with clinicians and we customize our printers according to their requirements in point of care delivery. And one such example is our this MRF project that we've got, where we work with Professor Fiona Wood in the University of Western Australia, where we are working on optimizing a preclinical model for 3D skin printing, especially for wound healing. So these two printers, the 3D Ready printer and the Biopen, they're the two printers that we're using for this project.
This is a printer?
It is.
Wow.
Yeah, so this is a handheld printer. The beauty of this printer is that we can, obviously this is very simple and small. We can take this to the operating theatre, and then we can print the biomaterial and the cells directly onto the wound site of the patients. And also this 3D Ready printer, we can have this set up in the operating theatre and then print the bioscaffolds and then directly transplant them onto the wound site of the patient. Yeah. And also, as you can see, these two printers are very compact, small, and very easy to operate. And these can be definitely transported to the end user facility, and say that could be an operating theatre of a hospital or to a PC2 laboratory in a research institute or maybe to outer space.
Yeah, I mean, it sounds like this could be a very powerful tool in a space environment. It's compact, it's probably quite low power. And then if you wanted to do something larger, you could use this. And I think it would be very interesting to fly printers like these and see how they respond to zero gravity, I'm guessing. We had a question from our audience, which was, I can see you have a Lithos system for ceramic printing. Can you provide a little bit more info on the process?
Yes, certainly. So we do have a Lithos system. The Lithos system is actually a COVID baby. It was delivered to us in March of last year.
Let's go take a look.
So we've got some very nice samples here that Sam may be able to zoom in on. And I like the fact that they're really small samples, so you can see the level of detail that's possible.
Obviously, scale my finger.
Obviously, you're aware of Lithos, so you understand that it's a DLP type process where you produce a green part with a band, or where the ceramic is bound with polymer. That printed part is then transferred to a debinding station where it's debound for a number of days at 800 degrees Celsius, and then transferred to a sintering station where it's sintered for another 48 hours at elevated temperatures of about 1200 degrees. At the moment, we're doing a lot of work in the development of complex multi-material extrusion tips. The benefit of this for us over our existing metal selective laser metal process is that we can have much finer surface finishes down below 2 micron. And in some cases, of some materials, they're quoting sub-micron surface roughnesses. That is a huge benefit to us, where previously we'd have surface roughnesses about 50 microns, which is possibly having an effect on the cells as we're printing.
Steve, can we get a shot of that alongside the metal one?
Yes, certainly.
So this is what you were talking about. So basically, whoops, gimbal doing a little flip there.
So the metal parts have been produced on some of the highest resolution selective laser melting tools in Australia. Originally, it was a Realizer SLM50. That system has now been superseded by Trump TruePrint 1000. That allows us to batch produce tips of a range of different geometries, either in a core shell configuration, as we use for the delivery of stem cells in the cartilage project, or in a side-by-side Janus type structure, where we want to put down multiple materials at a higher flow rate, but have a supporting material carrying a cell-laden material.
So again, another of our audience has asked, so you can create, this is from Christophe Grenet, thanks Christophe, so you can create material with artificial dielectric constant using ceramic 3D printing.
So we haven't gone down that pathway so far. What we want to be able to do is use the alumina oxide for some very specific biological projects that we're working on. And as we are expanding our knowledge on the system, and I'll be completely honest, there is a strong learning curve on this system. It is quite different to some of our other additive fabrication tools. We're now gravitating more so towards tricalcium phosphate and hydroxyapatite slurries as our building materials.
So one of our audience members, Philip, who is from High Tech Materials Proprietary Limited, if Philip wanted to come and have a chat to you, go a little bit deeper into how you're using the machine, is that something he can do?
I'm more than happy to, for anyone to contact me. We can arrange tours of the facility, and anyone who's been here before should always revisit, because we're constantly updating the hardware and our capabilities.
So, Steve, just before we go, we might mention we looked at the commercial robotic arm printer over in the other laboratory, and just what our intention is, particularly around the wound healing project.
Absolutely. So, unfortunately, I used the word absolutely live on TV again, but then I used gravity as well. Did I? That's shocking. I actually used a legitimate word. So what we have here is a 6-axis robotic arm system. It's an ABB IRB20. It's very much so an industrial robot. As an industrial robot, it's limited in the functionality that we can have, where we want to be able to deposit materials across complex structures and rather than on a planar substrate. What we're doing now, and what we've just invested in, is a KUKA LBR Med system. That's a full 7-axis medically certified robot. So it's got ISO 13485 certification right up to the end effector. That's going to allow us to couple devices like the Bio-pen or indeed other platforms that we're working on to allow us to conformably print onto more organic structures. So in the case of wound healing, where we would be able to take our wound healing materials, couple that to the delivery device, pre-scan the surgical area or the treatment area, and then deposit automatically onto that wound site.
Brilliant. Okay, well, thanks, Steve, and thanks, Kalani, for that amazing insights into what you see you can do with commercially available printers, and the expertise and the team that we have built in order to create customized printers for a range of applications, working with clinical collaborators. So again, that journey from fundamental discovery of materials, coupled with the best advances in fabrication in order to create real practical solutions, working very closely from day one with the end users of those technologies, and keen to engage with anyone who wants to get into that pipeline.
And we've got a fun, kind of nearly final question, because we're going to wrap soon. We're going to keep this tight. This is from Christophe. One of the crazy things we discussed once was the marriage of robotics and 3D printing to create a space spider that would 3D print structures in space. For example, mesh reflectors or solar panels or other structures. You know, is that something that you guys have had a chat about? What do you think, Steve? What do you think? Right? Coming nice and close so we can put them on the spot. You know, if you're moving the 3D printer around in space, you know, does that make things more complex, or is that just actually just a physical problem?
Say it's more of a physical problem. Say, for example, the biopen, we're using mechanical extrusion for that printer. So it all depends on the motors that it's got to operate the printer. And
it makes me think, right, we've got a 7-axis printer just next to you, and I'm thinking, well, what if 3 of those axes were, you know, a satellite system that could move around, or a robotic arm?
Yeah, it completely comes down to the application. So 3D printers are in 3D space because we're just using 3-axis stage. To have greater flexibility, yeah, certainly robotic arm in space is a fantastic idea, and there are many examples of extrusion-based printers based around robotic arm systems. But it comes down to the application, because it's not the conventional way of 3D printing. So it's not taking a slice and stacking slices. You have to have a much stronger development team in the software space where you can then plan the trajectories. So think of it more so like robotic weld. There's a marriage between 3D printing in space and robotic welding in space, because all of the pre-planning processes for welding are very similar to the processes for deposition of materials.
I love that you spoke about that, because one of the things that we are expecting is to need autonomous systems to plan the trajectory of a print, perhaps in an orbital servicing situation where the lag time is really high between the Earth and Mars, for example. So that path planning is a tooltip. That's another area of research for you guys.
That's something that Gordon may want to talk about, some of the AI work that we're doing in that kind of pre-planning of bioprint.
Yeah, we've developed over the last few years, Tim, a great collaboration with Svetlana Venkatesh in the area of machine learning, AI, and how we can use that in our conventional 3D printing and the optimization of those processes. So I think that team and that collaboration could really tackle some of those challenges you think of.
Fantastic. Well, so thank you so much, everybody. I'm just going to get the team. I'm going to take this off you, Sam, and I'm going to get the whole UOW University of Wollongong team in the same shot here. Sam, this is Sam, who's been your cameraman today, and Professor Gordon Wallace, here's Steve. Thank you very much, and here's Harani. And thank you so much for a terrific virtual walkthrough. We hope you've enjoyed it. We're going to, as I said, post this onto YouTube. We're keen to have this as a record of the facilities and capabilities that exist in the New South Wales space ecosystem. And I'm pretty keen to get these guys flown to space. So thank you so much for your attention, everybody, and your awesome questions. And say just a last wave from you guys.
Come and visit us.
Fantastic. We're going to wrap it up there. Thank you, folks.